So right here we have a sigmoid function. So simply put, the sigmoid is a function with infinite x values. So these x values here, actually, they continue forever. There are lines, but there's no limit on these x values, and y values between 0 and 1. So in other words, the sigmoid has a domain of negative infinity to positive infinity, and a range of 0 to 1. So this is actually the core reason we use a sigmoid. It's going to squish this large range of values, or maybe I should say large domain of values, and it's going to turn those into values between 0 and 1. But unlike your typical normalization of data, the sigmoid's actually characterized by its change in slope, or its derivative. So we see the derivative of a sigmoid. We like it for two reasons. Firstly, the high and low values, they all converge on about the same place without much change. So we can actually see this. Let's say this is 1, 2, 3, 4, 5, 6, 7, 8, 9. It's actually 9 squares. So we'll say that like right here is about 6. Maybe it's closer to 7, but it's about 6. And we say that this value is about 10. Now, if you actually find what these values are, you're going to see that the change is barely anything. It's maybe like 0.01. The change here is very, very slight. And this is from 6 to 10. Now, if we take that same change in x value, but we move it closer to 0, say the difference between 0 and 4, we see a much larger change. So 0 is always going to get mapped to 0.5. And 4, if we move that up, 4 is pretty much all the way up here at 0.8 or 0.9. So there's a much larger change between these lower values because you can see that this change in slope is just so much higher if you look at what the tangents would be than values at 6 and 10. So that's one reason we like the derivative. The other reason is if we actually take the derivative of this function, if we actually take it, we get an interesting type of metric known as the confidence. So even if you don't know how to take derivatives, and this is this first calculus bit, it's something I highly recommend learning. So I'm actually going to attach a video on how to take a derivative. It's actually very simple. Even if you don't know how to take derivatives, you can actually see that the halfway point in this in our data is going to be where the derivative is the highest. So we can actually sort of draw this out, and it's going to make this interesting curve. That's an awful curve. Anyways, that's good enough. I think you can get the picture of what this is trying to be. It's going to be sort of a curve that's going to level out at around 0 at these values, and then peak at 0 at 0. And so we can think of this as the confidence, which is something I'm going to get into in the next video on activation functions. But simply put, if you've got values that are closer to the middle of your data, they could tip either way. They're sort of at the tip of this derivative. You know, they could go either way. They could roll off either end of the hill. Whereas at the lower values, or at the very high values, you're pretty confident in whether you're classifying this as a 0 or as a 1. So anyways, the takeaways from this sigmoid is that the sigmoid maps all numbers between 0 and 1. The numbers at either extreme will be closer together, and the derivative of the sigmoid tells you how confident your network is on its output. So yeah, that's pretty much all you need to know to use in understanding sigmoid functions in relation to neural networks. So I hope this gave you maybe a little more understanding on what a sigmoid is, and maybe a little bit on why they were chosen as the flagship function of a neural network. And then in the next video, which weights and activation functions, I hope you might understand a little bit more about that why piece. So as an activity before you go, I want you all to write a function which takes the x value and Boolean as inputs. And if that Boolean is false, return the y value of the sigmoid at the given x. And if the Boolean is true, return the derivative of the sigmoid at the given x. And for bonus points, try to graph these graphically represent these as well. So draw the sigmoid as a point. Draw a point on the sigmoid for the y value, or maybe the tangent line for the derivative. So I'm going to include a Colab document with all of this written below. But next video, we're going to get into weights and activation functions. So I'm very excited to do that.